Right now, at this very moment, you are hurtling through space at approximately 67,000 miles per hour. You're riding on a blue marble that spins through the cosmic dark, carried by forces so vast and elegant that they've been shaping the universe for billions of years. Yet here you are, perfectly comfortable, breathing easily, held gently to the surface of this spinning world by an invisible embrace we call gravity. Welcome to Sleep About Science. I'm your sleepy scientist, and tonight we're exploring the remarkable science behind space travel. We'll journey from the earliest dreams of leaving Earth to the intricate ballet of physics that makes it possible for humans to slip the bonds of our home planet and venture into the infinite. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, it's exactly what this space is designed for. Before we begin our gentle voyage through the cosmos, please make yourself comfortable. Pull your blankets a little closer, adjust your pillow, and let your body settle into whatever position feels most restful. Remember, this is educational content, not medical advice, and there's no pressure to remember every detail. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into the sciences that shape our world. Now close your eyes if you'd like, and imagine for a moment that you're looking up at the night sky. Wherever you are in the world right now, whether it's evening or morning, day or night in your corner of our spinning planet, picture those distant points of light scattered across the darkness. For thousands of years, humans have gazed upward and wondered what would it be like to leave this world behind? What would it take to join those stars? The dream of space travel is as old as human curiosity itself, but the science that makes it possible is a story of physics so elegant and forces so precisely balanced that it almost seems like the universe conspired to make it possible for small, fragile beings like us to venture beyond our earthly home. Let's begin with the most fundamental challenge of space travel: escape velocity. Picture yourself standing on the surface of our planet, looking up at the sky. You are sitting at the bottom of what physicists call a gravity well, an invisible valley carved by the mass of the Earth itself. Every object with mass creates this kind of depression in the fabric of space and time, and the more massive the object, the deeper the well. Earth, with its substantial mass, creates quite a deep well indeed. To leave this well, to truly escape Earth's gravitational embrace, you need to achieve a very specific speed, approximately 25,000 miles per hour, or about 11 kilometers per second. This is escape velocity, and it represents one of the most beautiful concepts in physics. It's the speed at which an object must travel to break free from Earth's gravitational field without any additional propulsion. Think of it like throwing a ball into the air. Throw it gently, and it arcs up and falls back down. Throw it harder, and it goes higher before gravity wins and pulls it back. But there's a threshold, a precise speed where if you could somehow throw that ball fast enough, it would keep going up and up, never to return. That speed is escape velocity. But here's where the poetry of physics becomes apparent. Escape velocity doesn't depend on the mass of the object you're trying to launch. A grain of sand and a massive spacecraft both need to achieve the same speed to escape Earth's pull. It's not about the size or weight of what you're sending to space. It's about the energy you can give it, the speed you can help it achieve. Now imagine the challenge this presents. How do you accelerate something to 25,000 miles per hour? How do you give an object enough energy to climb out of Earth's gravitational well? The answer lies in one of humanity's oldest discoveries: the rocket. The principle behind rocket propulsion is beautifully simple, embodied in Isaac Newton's third law of motion. For every action, there is an equal and opposite reaction. When you walk across a room, you push against the floor, and the floor pushes back against you. When a rocket burns fuel and expels hot gases downward at tremendous speed, those gases push back against the rocket, driving it upward. But here's what makes rockets particularly elegant for space travel. They don't need anything to push against except their own exhaust. Unlike a car that needs roads or an airplane that needs air, a rocket carries everything it needs. It's a self-contained system, a little pocket of Earth's atmosphere and fuel that can operate in the vacuum of space. Picture a rocket on the launch pad, towering against the sky. Most of what you're seeing isn't the spacecraft itself, but fuel, enormous amounts of fuel. The Apollo Saturn V rocket, which carried astronauts to the moon, weighed about 6.2 million pounds when fully fueled, but the actual command module that housed the astronauts weighed only about 13,000 pounds. The vast majority of that towering structure was simply fuel and the containers to hold it. This is because of something called the rocket equation, or Tsiolkovsky's equation, named after Konstantin Tsiolkovsky, a Russian schoolteacher who dreamed of space travel in the late 1800s. The equation reveals a harsh truth about rockets. To go faster, you need more fuel, but more fuel makes your rocket heavier, which means you need even more fuel to accelerate that heavier rocket, which makes it heavier still. It's a mathematical spiral that makes space travel extraordinarily challenging. Tsiolkovsky calculated that to escape Earth's gravity, a single-stage rocket would need to carry about 90% of its mass as fuel. Imagine trying to drive a car that was 90% gasoline tank. This is why rockets are built in stages, each one designed to burn its fuel and then drop away, leaving the remaining stages lighter and more capable of acceleration. Let's follow a spacecraft's journey from Earth to space and feel the forces involved. As the rocket engines ignite, tremendous amounts of chemical energy convert to kinetic energy. Liquid oxygen and rocket fuel combine in a controlled explosion, creating temperatures hot enough to melt copper, generating exhaust gases that stream downward at speeds of up to 10,000 miles per hour. The rocket begins to rise, slowly at first, fighting against Earth's gravity. In those first moments, the acceleration is gentle, perhaps only 1.5 times the force of gravity. The astronauts inside feel pressed into their seats, but not uncomfortably so. As fuel burns and the rocket becomes lighter, the acceleration increases. By the time the first stage burns out and separates, the astronauts might experience forces 3 or 4 times stronger than Earth's gravity. But here's something wonderful to consider. As the rocket climbs higher, Earth's atmosphere becomes thinner. The air that once resisted the rocket's passage begins to fade away. About 60 miles up, the atmosphere is so thin that it's essentially gone. The sky that was blue at launch has faded through deeper and deeper shades until it becomes the absolute black of space. Now our spacecraft is in what we call low Earth orbit, traveling at approximately 17,500 miles per hour, fast enough to circle our entire planet in about 90 minutes. But it's not really weightless, as we often imagine. Gravity at the altitude of the International Space Station is still about 90% as strong as it is on Earth's surface. The sensation of weightlessness comes not from the absence of gravity, but from constantly falling. Picture this: the spacecraft and everything inside it, including the astronauts, are all falling toward Earth together, but they're moving so fast horizontally that they keep missing the planet. They fall in a perfect arc that matches Earth's curvature. It's like throwing a ball so hard that by the time it would hit the ground has curved away beneath it. This is orbital mechanics in its purest form. The spacecraft is in a delicate balance between its forward momentum, which wants to carry it in a straight line out into space, and Earth's gravity, which wants to pull it down. The result is a graceful curve and endless fall that never reaches the ground. From this vantage point, orbiting Earth at 17,500 miles per hour, our planet appears as it truly is, a small blue marble suspended in infinite black. The atmosphere that seems so substantial from the ground reveals itself as the thinnest of shells, no thicker relative to Earth than the skin of an apple. The boundaries between countries disappear. The lights of cities twinkle like stars scattered across the dark side of the planet. Weather systems swirl in magnificent spirals across continents. But low Earth orbit is just the beginning of space travel. To venture further, to reach the moon or other planets, spacecraft must master additional layers of physics and overcome new challenges. To leave Earth orbit and travel to another celestial body, a spacecraft must increase its speed even further, to about 25,000 miles per hour. This is where we encounter the concept of transfer orbits, elegant mathematical curves that spacecraft follow as they navigate between worlds. The most efficient path between Earth and another planet isn't a straight line, but a graceful arc called a Hohmann transfer orbit. Picture 2 planets orbiting the Sun at different distances, like runners on different lanes of a circular track. To move from the inner lane to the outer lane, you don't run straight across. Instead, you accelerate at just the right moment to enter an elliptical path that intersects both orbits at precisely the right times. This is the dance of interplanetary travel. Mission planners must calculate not just where a planet is when the spacecraft launches, but where it will be months or years later when the spacecraft arrives. They're essentially throwing a dart at a moving target, except the dart takes months to reach the target, and both the dart and the target are moving through 3-dimensional space at thousands of miles per hour. Consider the journey to Mars. Earth and Mars align favorably for such a journey only once every 26 months. When the planets reach positions that allow for the most efficient transfer orbit, miss this window and you must wait more than 2 years for the next opportunity, or accept a much longer, more expensive journey. The physics of such a journey reveals the elegant clockwork of our solar system. As a spacecraft travels from Earth to Mars, it's essentially changing its orbit around the Sun. It starts in Earth's orbit, moving at about 67,000 miles per hour relative to the Sun, and must adjust its speed and trajectory to intersect with Mars's orbit, where it will be moving at about 54,000 miles per hour. Throughout this journey, the spacecraft is subject to the gravitational influence of multiple bodies simultaneously. Earth's gravity dominates early in the flight, then gradually gives way to the Sun's influence. And finally, as the spacecraft approaches Mars, that planet's gravity begins to take hold. It's a delicate transition between spheres of influence, each celestial body passing the spacecraft along like a cosmic relay race. But let's pause here and consider the human element of space travel, because the physics that govern rockets and orbital mechanics are only part of the story. Humans are not naturally designed for the environment of space, and keeping people alive beyond Earth requires solving problems that range from the straightforward to the profoundly complex. In the weightlessness of space, the human body begins to change almost immediately, without gravity constantly pulling blood toward their feet. Astronauts' cardiovascular systems must adapt to a new reality. Blood redistributes throughout the body, causing faces to appear puffy and legs to become thin. The heart, no longer working against gravity, begins to weaken like any unused muscle. Bones, too, respond to the absence of gravitational stress. On Earth, the constant pull of gravity stimulates bone formation. In space, this stimulus disappears, and bones begin to lose density at a rate of about 1 to 2% per month. Muscles, particularly those in the legs and back that normally fight against gravity, begin to atrophy. These changes present one of the greatest challenges for long-duration space travel. A journey to Mars might take 6 to 9 months each way, with a stay on the planet's surface lasting 12 to 18 months. By the time astronauts return to Earth, their bodies would be profoundly changed by their time in weightlessness. Space agencies have developed countermeasures, specialized exercise equipment, medications, and carefully designed routines that help astronauts maintain their physical condition. But these are imperfect solutions to a fundamental mismatch between human biology and the space environment. There's also the psychological dimension of space travel. Imagine being confined in a space smaller than most apartments, with the same few people for months or years, knowing that Earth is just a blue dot in the darkness outside your window, knowing that if something goes wrong, help is impossibly far away. The isolation is profound. Radio signals between Earth and Mars can take anywhere from 4 to 24 minutes to travel one way, depending on the planet's positions in their orbits. This means that a simple conversation becomes impossible. Questions must be sent and answers waited for, like messages in bottles cast across an ocean of space. Yet despite these challenges, humans have not only survived in space but thrived there. They've conducted experiments that are impossible on Earth, made discoveries that have advanced our understanding of physics, biology, and medicine, and demonstrated a remarkable capacity to adapt to environments for which evolution never prepared them. The International Space Station, humanity's continuously inhabited outpost in low Earth orbit, represents one of the greatest cooperative achievements in human history. It's a testament to the power of international collaboration and human ingenuity. For more than 2 decades, humans have lived and worked aboard this laboratory, conducting thousands of experiments, maintaining and upgrading their orbital home, and proving that human presence in space is not just possible but valuable. Living aboard the space station requires mastering the physics of everyday activities in weightlessness. Simple tasks like eating, sleeping, or going to the bathroom become complex engineering problems. Water doesn't pour from a cup, but forms spheres that float freely through the air. Fire burns differently, forming perfect spheres instead of the teardrop shapes we see on Earth. Even tears behave strangely, forming bubbles around astronauts' eyes instead of flowing down their cheeks. These seemingly simple differences reveal fundamental aspects of physics that gravity normally obscures. In weightlessness, we can observe how fluids behave when only surface tension and molecular forces shape them, how heat transfers when there's no convection to carry it away, how crystals grow when there's no gravitational settling to interfere with their formation. Many of the experiments conducted in space take advantage of this unique environment to advance our understanding of materials, science, biology, and physics. Proteins can be crystallized more perfectly in weightlessness, potentially leading to better drugs. Metal alloys can be formed with more uniform properties. Plants can be studied to understand how they sense and respond to gravity on Earth. But perhaps the most profound impact of space travel isn't technological but philosophical. When astronauts look back at Earth from space, many report experiencing what's called the overview effect, a cognitive shift in awareness that comes from seeing our planet as it truly is, a single fragile oasis of life suspended in the infinite darkness of space. From space, Earth's atmosphere appears impossibly thin, its biosphere obviously delicate, its political boundaries meaningless. The planet looks exactly like what it is, the only home humanity has ever known, a small island of warmth and life in an ocean of cold emptiness. This perspective has inspired environmental movements, influenced art and literature, and changed the way humans think about their relationship with their home world. As we look toward the future of space travel, new technologies are emerging that may overcome some of the current limitations. Ion drives, which use electric fields to accelerate small particles to extremely high speeds, can provide continuous, gentle thrust for months or years, gradually building up to tremendous velocities while using minimal fuel. Solar sails, gossamer sheets of reflective material kilometers across, can be pushed by the pressure of sunlight itself, requiring no fuel at all for propulsion. These technologies work slowly, taking months or years to accelerate spacecraft to high speeds, but they offer the possibility of efficient, long-duration missions to the outer solar system and beyond. Nuclear propulsion, either in the form of nuclear thermal rockets or nuclear electric systems, could provide the high specific impulse needed for faster travel to Mars and the outer planets. These systems could reduce travel times, making human missions more feasible and safer. Even more speculative technologies like fusion rockets or antimatter drives exist in the realm of theoretical possibility, offering the potential for spacecraft that could reach significant fractions of the speed of light, making interstellar travel conceivable within human lifetimes. But for now, chemical rockets remain our primary means of escaping Earth's gravity and venturing into space. Despite their limitations, they've carried humans to the moon, delivered telescopes that have revolutionized our understanding of the universe, and sent robotic explorers to every planet in our solar system. These robotic ambassadors have been extraordinary pioneers, venturing where humans cannot yet safely travel. They've landed on Mars and analyzed its soil, flown through the ice geysers of Enceladus, orbited Jupiter and Saturn for years, and traveled to the very edge of our solar system and beyond. The Voyager spacecraft, launched in 1977, are now traveling through interstellar space, carrying golden records with sounds and images from Earth, as messages to any intelligent life they might encounter. They represent humanity's first tentative steps into the galaxy, our first artificial objects to leave the solar system and venture into the space between the stars. Consider the physics of their journey. After more than 40 years of travel, they're now more than 14 billion miles from Earth, so far away that radio signals take more than 20 hours to reach them. They're traveling at about 38,000 miles per hour relative to the Sun, fast enough to cross the United States in about 4 minutes, yet at this speed it would take them more than 70,000 years to reach the nearest star. This gives us a sense of the true scale of space and the challenges of interstellar travel. The distances between stars are so vast that they challenge human comprehension, even traveling at the speed of light, which physics tells us is impossible for anything with mass. It would take more than 4 years to reach the nearest star. Yet the same physics that reveals these daunting challenges also suggests possibilities. Einstein's theory of relativity shows us that space and time are not fixed but can be warped and stretched. While we cannot exceed the speed of light, there may be ways to effectively travel faster than light by manipulating space-time itself, perhaps through concepts like wormholes or warp drives that exist in the mathematical framework of general relativity. These remain highly speculative, requiring exotic forms of matter and energy that we have no idea how to create or control. But the history of space travel shows us that today's impossible dreams can become tomorrow's routine achievements. The rockets that carry astronauts to the International Space Station would have seemed like pure fantasy to most people just a century ago. The science behind space travel is ultimately the science of dreams made real through patient application of physical principles. It's the story of humans who looked up at the stars and refused to accept that they were forever beyond reach. It's the tale of how curiosity and mathematics and engineering came together to solve one of the most fundamental challenges imaginable, escaping the bonds of Earth and venturing into the cosmic dark. Every spacecraft that leaves Earth carries with it the accumulated wisdom of thousands of years of human observation and understanding. From ancient astronomers who mapped the movements of planets to modern physicists who calculated the curvature of space-time, each contributed to our growing ability to navigate the universe. The rockets themselves are marvels of engineering, representing some of the most complex machines ever built. A single space shuttle had more than 2.5 million parts, each designed and tested to operate reliably in the harsh environment of space. The Saturn V rocket that carried astronauts to the Moon generated 7.6 million pounds of thrust, enough to lift a fully loaded aircraft carrier. Yet for all their complexity, these machines operate on principles that are beautifully simple. They push against their own exhaust to generate thrust. They follow the graceful mathematics of orbital mechanics. They balance the fundamental forces of gravity and momentum in an eternal dance around celestial bodies. The human story of space travel is also a story of international cooperation. The International Space Station involves space agencies from the United States, Russia, Europe, Japan, and Canada. Astronauts from dozens of countries have lived and worked together in space, demonstrating that some human endeavors transcend national boundaries and political differences. This cooperation extends to robotic exploration as well. Spacecraft from different nations have worked together to study planets, moons, and asteroids. Data is shared freely among the international scientific community, advancing our collective understanding of the solar system and universe. As you lie there, perhaps growing drowsy, consider that the same forces that hold you gently against your bed extend throughout the universe. Gravity, the force that keeps your blankets pressed against you, is the same force that holds planets in their orbits, binds galaxies together, and shapes the large-scale structure of the cosmos. The atoms in your body were forged in the nuclear furnaces of stars scattered through space when those stars died, and eventually incorporated into the planet Earth and ultimately into you. In a very real sense, you are made of star stuff, and space travel is simply a homecoming, a return to the cosmic environment from which we all came. The oxygen you breathe was created in the cores of massive stars. The iron in your blood was forged in the incredible violence of stellar explosions called supernovae. The calcium in your bones, the carbon in your cells, the phosphorus in your DNA, all of it was created in stellar furnaces and scattered across the galaxy by cosmic winds. This means that space travel isn't just a technological achievement, but a kind of cosmic reunion. When humans venture into space, they're returning to the environment where the very elements of their being were created. The spacecraft that carry them are made of materials that were likewise forged in stars, using principles of physics that apply throughout the universe. The same laws of motion that govern a rocket's flight also govern the dance of binary stars, the collision of galaxies, and the expansion of the universe itself. The electromagnetic forces that hold atoms together in spacecraft materials are the same forces that power the sun and create the aurora that dance in Earth's atmosphere. This universality of physical law is one of the most profound discoveries of modern science. The physics we study on Earth applies everywhere in the universe. The same periodic table of elements exists on distant planets. The same mathematical relationships describe the behavior of matter and energy, whether we're in a laboratory on Earth or in the depths of interstellar space. This gives us confidence that the technologies we develop for space travel will work as expected in the cosmic environment. A rocket engine that operates according to Newton's laws on Earth will operate the same way on Mars or in the asteroid belt. Solar panels that convert sunlight to electricity near Earth will do the same, though less efficiently near Jupiter. It also means that the scientific discoveries we make through space exploration have universal significance. When we study how materials behave in the weightlessness of the space station, we're learning about fundamental properties of matter that apply throughout the cosmos. When we analyze the composition of asteroids or the atmospheric dynamics of other planets, we're gaining insights that help us understand our own world. Space travel has also given us new perspectives on time itself. Einstein showed us that time is not absolute but relative, flowing differently for observers in different gravitational fields or moving at different speeds. While these effects are tiny for most space missions, they become significant for spacecraft traveling at very high speeds or operating in strong gravitational fields. The GPS satellites that help us navigate on Earth must account for relativistic effects. Time runs slightly faster for these satellites in their high orbits where Earth's gravity is weaker, and they're moving at high speeds relative to observers on the ground. Without corrections for these relativistic effects, GPS would accumulate errors of several miles per day. For future missions to other stars, these effects could become profound. A spacecraft traveling at speeds approaching the speed of light would experience time dilation, where time aboard the ship passes more slowly than time on Earth. Crew members might age only months or years during a journey that takes decades or centuries as measured by Earth-based observers. This creates fascinating paradoxes and possibilities. Interstellar travelers might return to Earth to find that hundreds of years have passed while they've aged only slightly. They would become time travelers journeying not just through space but through time itself. These concepts stretch our imagination and challenge our intuitive understanding of reality. yet they're firmly grounded in physics that has been tested and verified countless times. The mathematics of relativity is as solid as the mathematics that describes the orbit of the Moon or the trajectory of a spacecraft traveling to Mars. As space technology advances, we may need to grapple more directly with these relativistic effects. Fusion-powered spacecraft could potentially achieve speeds that are significant fractions of light speed, making time dilation noticeable. Missions to explore the space around black holes would encounter extreme gravitational fields where time flows dramatically differently than it does near Earth. The study of space travel has also revealed the incredible precision required for interplanetary missions. When spacecraft travel to other planets, they must be aimed with extraordinary accuracy across distances of millions or billions of miles. It's like shooting an arrow from New York to Los Angeles and hitting a target the size of a dinner plate, except the target is moving, the archer is moving, and the arrow must travel for months before arriving. This precision is achieved through careful application of orbital mechanics, the branch of physics that describes how objects move under the influence of gravity. Every planet, moon, and asteroid in the solar system follows predictable paths governed by the same mathematical principles that Newton discovered more than 3 centuries ago. Mission planners use these principles to calculate trajectories years in advance, plotting courses that will take spacecraft exactly where they need to be at exactly the right time. They must account for the gravitational influence of every significant body in the solar system, the pressure of solar radiation on the spacecraft, and even tiny forces like the uneven heating of the spacecraft by sunlight. Sometimes they can use the gravity of planets as aids rather than obstacles, employing gravitational assists or slingshot maneuvers to accelerate spacecraft and change their trajectories. The Voyager missions used a rare alignment of the outer planets to visit Jupiter, Saturn, Uranus, and Neptune in a single grand tour that would have been impossible with conventional propulsion alone. These gravitational assists demonstrate the elegant interconnectedness of celestial mechanics. By carefully timing their approach to a planet, spacecraft can steal a tiny amount of the planet's orbital energy, gaining speed while imperceptibly slowing the planet itself. It's a cosmic trade that allows us to reach the outer solar system with much less fuel than would otherwise be required. The mathematics of these maneuvers are beautiful in their complexity and precision. Mission planners must solve multi-body gravitational problems, account for relativistic effects, and optimize trajectories for fuel efficiency, travel time, and scientific objectives. The calculations involved would fill libraries, yet they result in spacecraft that arrive at their destinations with accuracies measured in kilometers after journeys of billions of miles. Consider the Cassini mission to Saturn, which launched in 1997 and arrived at the ringed planet in 2004. During its journey, Cassini performed gravitational assists at Venus twice, Earth and Jupiter, following a complex trajectory that took it on a 7-year journey through the inner and outer solar system. When it finally arrived at Saturn, it was positioned so precisely that it could enter orbit around the planet and begin a 13-year exploration of the Saturnian system. During those 13 years, Cassini revolutionized our understanding of Saturn, its rings, and its moons. It discovered geysers of water erupting from the moon Enceladus, revealing a subsurface ocean that might harbor life. It studied the thick atmosphere of Titan, Saturn's largest moon, and deployed a probe that landed on Titan's surface. It observed the intricate dynamics of Saturn's rings, revealing them to be far more complex and active than previously imagined. All of this was possible because of the precise application of physical principles, the gravitational dance that brought Cassini to Saturn, the radio communications that carried data across billions of miles, the nuclear power source that provided electricity for 20 years, and the sophisticated instruments that translated electromagnetic radiation into scientific knowledge. The end of Cassini's mission was as precisely calculated as its beginning. In 2017, with its fuel running low, mission controllers directed the spacecraft to plunge into Saturn's atmosphere, ensuring that it wouldn't accidentally crash into one of Saturn's moons and potentially contaminate them with earthly microbes. Even in death, Cassini served science, transmitting data about Saturn's atmosphere until the very last moment before it was destroyed by the intense heat and pressure. This attention to planetary protection reflects another important aspect of space exploration, our responsibility to preserve the cosmic environment for future exploration and to avoid contaminating other worlds with life from Earth. This is both a practical and ethical consideration, ensuring that when we do discover life elsewhere in the universe, we can be confident it's truly alien and not a hitchhiker from our own planet. The search for life beyond Earth is one of the most compelling motivations for space exploration. While we haven't yet found definitive evidence of life elsewhere, Space missions have revealed that the conditions for life might be more common than we once thought. Water in liquid form appears to exist beneath the icy surfaces of several moons in our solar system, including Europa around Jupiter and Enceladus around Saturn. Mars shows clear evidence of having had liquid water on its surface in the distant past, with ancient riverbeds, lake beds, and mineral formations that could only have formed in the presence of water. Current missions are searching for signs of past or present microbial life in Martian soil and rocks. The discovery of life beyond Earth would be one of the most profound scientific findings in human history, fundamentally changing our understanding of our place in the universe. It would suggest that life is not a unique accident that occurred only on Earth, but perhaps a common feature of planets with suitable conditions. Even if life beyond Earth remains elusive, the search itself has advanced our understanding of biology, chemistry, and planetary science. The extreme environments that spacecraft encounter in space and on other worlds have expanded our concept of where life might be possible, leading to the discovery of extremophile organisms on Earth that thrive in conditions once thought to be completely hostile to life. These discoveries have implications beyond space exploration. Understanding how life might survive in the harsh environment of space could inform efforts to preserve life on Earth in the face of climate change and other environmental challenges. The closed-loop life support systems developed for spacecraft could inspire more sustainable technologies for use on our home planet. The technology developed for space exploration has had countless applications in everyday life on Earth. The miniaturized electronics required for spacecraft have contributed to the development of computers, smartphones, and countless other devices. Materials science advances driven by the need to build lightweight, strong components for rockets and spacecraft have led to new composites and alloys used in everything from automobiles to sporting goods. Medical technologies developed to monitor astronaut health in space have found applications in hospitals and clinics. Water purification systems designed for spacecraft have been adapted to provide clean water in remote or disaster-affected areas on Earth. Weather satellites provide crucial data for agriculture, disaster preparedness, and climate research. Perhaps most importantly, space exploration has given us a new perspective on Earth itself. Satellites monitoring our planet's atmosphere, oceans, and land surfaces provide data that is essential for understanding and addressing climate change. From space, we can see the global nature of environmental challenges and monitor changes that are difficult to detect from ground-based observations. The images of Earth from space, from the first fuzzy black and white photographs to today's high-resolution color images, have had a profound impact on human consciousness. They've made real the concept that we all share one small planet, that national boundaries are human constructs, and that the health of our global environment affects us all. This perspective has been called the overview effect, and it represents perhaps the most important contribution of space exploration to human civilization. It's a shift in consciousness that comes from seeing Earth as it truly is, a small, fragile, beautiful world suspended in the infinite darkness of space, the only home humanity has ever known. As you rest there, breathing quietly, consider that the air filling your lungs has been recycled through the global atmospheric system countless times. The oxygen you're breathing might once have been breathed by a dinosaur or ancient tree or someone on the other side of the world. The water in your body has fallen as rain, flowed in rivers, and evaporated from oceans in an endless cycle that connects all life on Earth. From space, these connections become visible. Astronauts report seeing the thin blue line of Earth's atmosphere and realizing how delicate it is, how precious, how deserving of protection. They see weather systems swirling across continents, carrying water from the oceans to replenish inland areas. They see the lights of cities connected by highways and shipping routes, revealing the web of human civilization. But they also see the darkness between the stars, the vast emptiness that surrounds our small planet. This darkness is not empty but filled with wonders. Distant galaxies containing billions of stars, nebulae where new stars are born, and planets orbiting other suns that might, like Earth, harbor life. The space telescopes we've launched have revealed some of these wonders, peering deeper into space and further back in time than ever before. They've shown us that the universe is not only larger than we imagined, but also more strange and beautiful. They've discovered planets around other stars, some of which might have conditions suitable for life as we know it. These discoveries raise profound questions about our place in the cosmos. Are we alone, or is life common throughout the universe? Are there other civilizations among the stars, perhaps far more advanced than our own? What would it mean for humanity to make contact with intelligent life from another world? The physics that govern space travel suggests that interstellar distances are so vast that direct contact between civilizations might be extremely rare, even if life is common. The nearest star is more than 4 light-years away, meaning that even a radio signal travels for more than 4 years to reach it and more than 8 years for a round-trip communication. A physical journey to another star would require either technologies far beyond our current capabilities or a willingness to undertake voyages lasting thousands of years. Generation ships, spacecraft designed to support human populations for many centuries, remain in the realm of science fiction, though they're not forbidden by the laws of physics. Perhaps more plausibly, we might one day send robotic probes to nearby stars, tiny spacecraft accelerated to high speeds by powerful lasers or other advanced propulsion systems. These probes could beam back data about other solar systems, searching for signs of life or habitable planets. Even this represents an enormous technological challenge. A probe traveling at 10% the speed of light would take more than 40 years to reach the nearest star, and its radio signals would take another 4 years to return to Earth. The probe would need to be incredibly robust to survive decades in the harsh environment of interstellar space, and it would need to operate autonomously, making decisions without guidance from Earth. Yet such missions are being seriously studied by space agencies and private organizations. The prospect of actually exploring other solar systems, of answering the question of whether life exists elsewhere in the universe, is compelling enough to drive continued research into advanced propulsion technologies and miniaturized spacecraft. Meanwhile, closer to home, the exploration of our own solar system continues. Missions are planned or underway to visit every planet, and many of their moons and asteroids. Each mission reveals new wonders and raises new questions about the formation and evolution of our solar system. The physics principles that enable these missions remain the same ones that have guided space exploration since the beginning: Newton's laws of motion, conservation of energy and momentum, and the elegant mathematics of orbital mechanics. But our application of these principles has become ever more sophisticated, allowing us to undertake missions of increasing complexity and ambition. Future missions might establish permanent human settlements on Mars, mine asteroids for valuable resources, or explore the subsurface oceans of Europa and Enceladus in search of life. Each of these endeavors will require advances in technology, but they're all achievable within the framework of known physics. The colonization of Mars represents one of the most significant challenges in space exploration. Unlike missions to the International Space Station or even the Moon, Mars is so far from Earth that rescue missions would be impossible, and communication delays would make real-time support from Earth impractical. A Mars colony would need to be largely self-sufficient, producing its own food, water, oxygen, and fuel. The thin Martian atmosphere, composed mostly of carbon dioxide, could potentially be processed to produce oxygen for breathing and methane for fuel. Water ice, abundant in Martian polar regions, and likely present as permafrost in many areas, could provide water for drinking and irrigation. The lower gravity on Mars, about 38% of Earth's gravity, would present its own challenges for human health and engineering. Construction techniques developed for Earth might not work the same way on Mars, and humans living there for extended periods would experience continued bone and muscle loss, though less severe than in the weightlessness of space. The psychological challenges of Mars colonization might be even more daunting than the physical ones. Colonists would be millions of miles from Earth, unable to return for years at a time due to the orbital mechanics that govern travel between the planets. The Martian day is about 24 hours and 37 minutes long, not far from Earth's day, but the seasons are nearly twice as long due to Mars's longer year. Despite these challenges, the physics of Mars colonization is well understood. The technologies needed, while advanced, are extensions of systems already used in space exploration. What's required is not new physics, but new engineering, new manufacturing capabilities, and new approaches to creating sustainable closed-loop life support systems. The asteroid belt, lying between Mars and Jupiter, represents another frontier for space exploration and potentially resource extraction. Asteroids contain enormous quantities of metals and other materials that are rare on Earth's surface, but essential for advanced technologies. A single large asteroid might contain more platinum than has ever been mined on Earth. The physics of asteroid mining presents unique challenges. Most asteroids are small bodies with very weak gravity, making it difficult for spacecraft to land on them and for mining equipment to operate effectively. Special anchoring systems and low-thrust propulsion would be needed to work in these environments. But the potential rewards are enormous, not just in terms of valuable materials, but in enabling further space exploration. Fuel and construction materials obtained from asteroids could support missions deeper into the solar system without the enormous cost of launching everything from Earth's surface. The outer planets and their moons represent the current frontier of robotic exploration, and they might someday host human missions as well. Jupiter's moon Europa and Saturn's moon Enceladus both appear to have liquid oceans beneath their icy surfaces, making them prime targets in the search for life beyond Earth. These missions would require new technologies to penetrate the ice shells and explore the subsurface oceans. Robotic submarines might one day swim in Europa's oceans, searching for signs of life in an environment that might be more hospitable than the surface conditions of Mars. The physics of these missions pushes the boundaries of current technology. The spacecraft would need to operate in the intense radiation environment around Jupiter, survive the long journey to the outer solar system, and function reliably in the extreme cold far from the Sun. As our understanding of physics continues to advance, new possibilities for space exploration may emerge. Quantum mechanics might someday enable new forms of propulsion or communication. Our growing understanding of dark matter and dark energy might reveal new ways to manipulate gravity or space-time. Even more speculative possibilities exist at the intersection of physics and biology. If we can understand how life works at the most fundamental level, we might be able to design organisms specifically adapted to space environments or develop new forms of life support that work more like ecosystems than machines. The exploration of space has always been about more than just the destinations we reach. It's about the journey itself, the process of discovery, the expansion of human knowledge and capability. Each mission teaches us something new about the universe and about ourselves. The men and women who venture into space, whether as astronauts on short missions or as future colonists on distant worlds, carry with them the accumulated wisdom of our species, our understanding of physics and chemistry and biology, our technologies and techniques, our hopes and dreams for the future. They also carry our responsibilities to explore space carefully and ethically, to preserve what we find there, to share the benefits of space exploration with all humanity, and to remember that no matter how far we travel, Earth remains our home and deserves our protection and care. As you drift towards sleep, perhaps you can imagine yourself as one of those future explorers, floating weightless in a spacecraft traveling between worlds, looking out at the stars and knowing that each point of light is a sun like our own, possibly surrounded by planets, possibly hosting life. The physics that makes such journeys possible is the same physics that governs everything around you right now. The electromagnetic forces holding your body together, the gravitational force pressing you gently into your bed, the thermodynamics that keeps your body warm, the quantum mechanics that enables the chemical reactions that sustain your life. You are already a space traveler, riding aboard Spaceship Earth as it spins and orbits through the galaxy. The air you breathe was processed by plants that learned to capture energy from our star. The food you eat was grown in soil, enriched by the decay of countless generations of life. The water you drink has been part of clouds and rivers and living things for billions of years. The same physical principles that will someday carry humans to the stars are already carrying you on an incredible journey through space and time. Right now, in this moment, you are part of an ongoing adventure that began with the Big Bang and will continue for billions of years into the future. Sleep well, fellow traveler. Dream of stars and planets, of spacecraft gracefully dancing through the solar system according to the elegant laws of physics, of humans taking their first steps on distant worlds, of discoveries that will transform our understanding of the universe and our place within it. And remember that the greatest journey is not necessarily the one that takes you farthest from home, but the one that helps you understand how remarkable it is that you exist at all, here on this small blue planet, conscious and curious, capable of understanding the physics that governs the cosmos, and of dreaming of adventures among the stars. The universe is vast and full of wonders, but there is nothing more wonderful than the fact that it has given rise to beings capable of contemplating it, exploring it, and finding their place within it. Sweet dreams, and may your rest be filled with the quiet satisfaction of belonging to this amazing cosmic story. But let's dive even deeper into the remarkable physics that makes space travel possible, exploring the subtle forces and elegant principles that most of us never stop to consider. Think about the moment just before a rocket launches, when it sits poised on the launch pad, every system perfectly balanced, waiting for ignition. In those final seconds, the spacecraft is held in place not by mechanical clamps, but by the fundamental force that governs everything in the universe, the electromagnetic force. The molecular bonds in the metal structure of the launch pad, the chemical bonds in the rocket fuel, even the electrical signals racing through the control systems, all depend on electromagnetic interactions between atoms and electrons. When the countdown reaches zero and ignition occurs, we witness one of the most dramatic demonstrations of chemistry and physics working together to overcome gravity. Consider the chemistry happening inside the rocket engines during those first moments of flight. In the combustion chamber of a liquid-fueled rocket, supercooled liquid oxygen meets refined kerosene or liquid hydrogen at temperatures cold enough to freeze the air around them. Yet when they mix in the controlled environment of the engine, they create a reaction hot enough to melt steel, reaching temperatures of over 6,000 degrees Fahrenheit. This is chemistry at its most extreme. The oxygen and hydrogen don't simply burn, they undergo rapid molecular reorganization, breaking apart and reforming in reactions that release enormous amounts of energy in incredibly short periods of time. Every second, a large rocket engine might consume tons of fuel, converting it into superheated gases that stream out of the engine nozzle at speeds that would make a supersonic jet seem leisurely. The shape of the rocket nozzle itself is a masterpiece of physics and engineering. It's designed according to principles of fluid dynamics that were worked out more than a century ago, but still represent some of the most elegant applications of thermodynamics you'll find anywhere. The nozzle starts narrow where the hot gases enter, then expands in a carefully calculated curve that accelerates the exhaust to maximum velocity. This expansion follows Bernoulli's principle, the same physics that creates lift on airplane wings and allows carburetors to work in automobile engines. As the cross-sectional area of the nozzle increases, the pressure of the gases decreases, but their velocity increases dramatically. It's a beautiful trade-off between pressure and speed that allows rockets to convert the thermal energy of combustion into the kinetic energy of directed motion. But even more fascinating is what happens to those exhaust gases after they leave the nozzle. At sea level, the hot gases slam into the atmosphere, creating the billowing clouds and thunderous noise we associate with rocket launches. But as the rocket climbs higher and the atmosphere becomes thinner, the exhaust plume changes dramatically. In the near vacuum of space, there's nothing for the exhaust to push against except itself, so it expands into a nearly perfect sphere of glowing particles, visible sometimes as an ethereal bubble of light surrounding the spacecraft. This transition from the dense, directed exhaust plume at sea level to the gossamer sphere in space perfectly illustrates the changing environment that spacecraft must navigate. The mathematics that describe these changes involve some of the most beautiful equations in physics. The Navier-Stokes equations, which describe fluid flow, combine with thermodynamic relationships to predict exactly how gases will behave under different conditions of temperature, pressure, and velocity. These equations are so complex that solving them exactly is one of the most challenging problems in mathematics. Yet rocket engineers use approximations of them to design engines that work with incredible precision. As our rocket climbs through the atmosphere, it encounters layers of air with dramatically different properties. Near the ground, the atmosphere is dense and rich in oxygen and nitrogen. At 20,000 feet, the air is thin enough that humans need supplemental oxygen. At 40,000 feet, the air pressure is so low that water would boil at room temperature. At 100,000 feet, the air is so thin that it barely deserves to be called an atmosphere at all. Each of these layers presents different challenges for a climbing spacecraft. In the dense, lower atmosphere, aerodynamic forces dominate, and the rocket must be designed to slip efficiently through the air without being torn apart by aerodynamic stress. Higher up, where the air is thinner, these forces diminish, but new challenges emerge. The transition through the atmosphere also affects the rocket's engines in subtle ways. Most rocket engines are optimized for the vacuum of space, where they can achieve their highest specific impulse, a measure of how efficiently they use fuel. At sea level, these same engines operate less efficiently because the atmospheric pressure working against the exhaust reduces their effectiveness. This is why many rockets use different engines for different parts of their flight, or engines that can adjust their performance as atmospheric conditions change. It's another example of how space travel requires not just brute force, but careful optimization of every system for the changing conditions of the journey. Once our spacecraft reaches the edge of space, officially defined as 100 kilometers above Earth's surface, it enters a realm governed almost entirely by gravitational physics. Here, in the near vacuum above the atmosphere, Newton's laws of motion reign supreme. An object in motion stays in motion, an object at rest stays at rest, and for every action there is an equal and opposite reaction. These simple principles, first articulated more than 300 years ago, provide the foundation for all space navigation. They tell us exactly how much velocity change is needed to alter a spacecraft's orbit, how gravitational forces from multiple bodies combine to influence trajectories, and how to calculate the precise timing needed for interplanetary missions. But while Newton's laws provide the framework, the actual calculations quickly become extraordinarily complex. A spacecraft traveling from Earth to Mars is influenced simultaneously by the gravitational fields of the Sun, Earth, Mars, Jupiter, and every other significant body in the solar system. Each of these influences is constantly changing as the planets move in their orbits. Computing a trajectory that accounts for all these influences requires solving what mathematicians call the n-body problem, one of the classic challenges in physics. For more than two bodies, there's no exact mathematical solution, so mission planners must use numerical methods, essentially having computers calculate the gravitational forces moment by moment throughout the entire journey. These calculations must be incredibly precise because tiny errors accumulate over the months or years of an interplanetary journey. A velocity error of just 1 meter per second during Earth departure could result in missing Mars by thousands of kilometers months later. This requires not just precise calculation but also continuous monitoring and course corrections throughout the flight. The spacecraft carries thrusters that can make small adjustments to its trajectory, but these corrections must be planned carefully because fuel is limited. Each course correction represents a trade-off between accuracy and efficiency, another optimization problem that mission planners must solve. During the long coast phase of an interplanetary journey, when the main engines are shut down and the spacecraft is essentially falling through space under the influence of gravity alone, other subtle forces begin to matter. Solar radiation pressure, caused by photons from the sun striking the spacecraft, can gradually alter its trajectory. For large spacecraft with solar panels, this force can be significant enough to require compensation. Even more subtle is the Yarkovsky effect, caused by thermal radiation from the spacecraft itself. As parts of the spacecraft heat up in sunlight and cool in shadow, they emit infrared radiation that can create tiny thrust forces. For small asteroids, this effect can significantly change their orbits over millions of years. For spacecraft, it's usually negligible, but mission planners still account for it in their most precise calculations. The cosmic environment that spacecraft travel through is far from empty. Even in the vacuum of interplanetary space, there are about 5 atoms per cubic centimeter, mostly hydrogen and helium, left over from the formation of the solar system. There's also a constant stream of high-energy particles from the sun called the solar wind, traveling at speeds of several hundred kilometers per second. This solar wind creates the heliosphere, a vast bubble of charged particles that extends far beyond the orbit of Pluto. The boundary where the solar wind meets the interstellar medium, called the heliopause, is where the Voyager spacecraft are now traveling, more than 40 years after their launch. Within the heliosphere, spacecraft must deal with radiation levels that would be lethal to unprotected humans. The electronics aboard spacecraft must be hardened against radiation, using special components and shielding to prevent cosmic rays from causing computer errors or equipment failures. The magnetic fields carried by the solar wind also interact with the magnetic fields of planets in complex ways. Earth's magnetic field deflects most of the solar wind, creating the magnetosphere that protects our planet's atmosphere from being stripped away. But this same magnetic field can trap high-energy particles, creating radiation belts that spacecraft must navigate carefully. Mars, with its much weaker magnetic field, offers little protection from solar radiation. This is one of the major challenges for future human missions to Mars: how to protect astronauts from radiation during the journey and on the planet's surface. The radiation environment varies dramatically depending on solar activity. During solar maximum, when the sun is most active, solar flares can release bursts of high-energy particles that would be dangerous to astronauts. During solar minimum, when the sun is quieter, cosmic rays from outside the solar system become more prominent. Mission planners must account for these cycles when designing long-duration missions. A journey to Mars that might be relatively safe during solar minimum could be much more dangerous during solar maximum. This adds another layer of complexity to mission planning, requiring not just precise orbital mechanics but also space weather forecasting. The spacecraft themselves must be marvels of engineering to survive in this hostile environment. Every component must function reliably for years without maintenance, in conditions of vacuum, extreme temperature variations, and constant radiation. Materials that work perfectly on Earth might become brittle in space, adhesives might outgas and contaminate sensitive instruments, and lubricants might freeze or evaporate. The power systems aboard spacecraft represent particularly elegant solutions to challenging physics problems. Solar panels must efficiently convert sunlight to electricity while remaining lightweight and resistant to radiation damage. Near Earth, where sunlight is abundant, this is relatively straightforward. But missions to the outer solar system, where sunlight is weak, require either enormous solar arrays or alternative power sources. Many deep space missions use radioisotope thermoelectric generators, devices that convert heat from radioactive decay directly into electricity. These systems use the thermoelectric effect, where temperature differences in certain materials create electrical voltages. They're incredibly reliable with no moving parts and can operate for decades. The nuclear batteries aboard the Voyager spacecraft, for instance, have been providing power for more than 40 years, though their output gradually decreases as the radioactive material decays. Mission planners must carefully manage this declining power, gradually shutting down non-essential systems to keep the most important instruments operating as long as possible. The communication systems that connect spacecraft with Earth represent another triumph of physics and engineering. Radio signals travel at the speed of light, which seems instantaneous for terrestrial communications, but becomes a significant factor for interplanetary missions. A radio signal from Mars can take anywhere from 4 minutes to 24 minutes to reach Earth, depending on the planet's positions in their orbits. This delay makes real-time control of spacecraft impossible. Instead, spacecraft must be largely autonomous, capable of making decisions and responding to problems without waiting for instructions from Earth. The radio signals themselves must overcome enormous challenges. By the time a signal from a spacecraft at Jupiter reaches Earth, it has traveled over 400 million miles, and its power has decreased by the inverse square of that distance. A transmitter that produces 20 watts at Jupiter delivers only a few billionths of a watt to receivers on Earth. Detecting these incredibly weak signals requires some of the most sensitive radio receivers ever built. The Deep Space Network, a collection of massive radio antennas in California, Spain, and Australia, can detect signals so weak that their power is less than the energy of a snowflake hitting the ground. These antennas must track spacecraft with extraordinary precision as Earth rotates and the spacecraft move through their orbits. The pointing accuracy required is like hitting a target the size of a penny from 1,000 miles away, and this must be maintained continuously as both the antenna and the target are moving. The data transmitted by these weak radio signals contains everything we know about the remote reaches of our solar system. Images of alien landscapes, measurements of atmospheric compositions, magnetic field data, and countless other scientific observations. Each bit of data represents a small victory over the vast distances and hostile environment of space. Some of the most profound discoveries in space exploration have come from measuring things that seem impossibly subtle. The Gravity Probe B mission, for instance, measured how Earth's rotation affects the fabric of space-time itself, detecting changes in the orientation of spinning gyroscopes that amounted to less than the width of a human hair over the course of a year. These measurements confirmed predictions of Einstein's general theory of relativity with extraordinary precision, demonstrating that massive rotating objects like Earth actually drag space-time around with them as they spin. It's an effect so small that it requires the near-perfect vacuum and weightlessness of space to measure accurately. Similarly, the ELISA Pathfinder mission tested technology for detecting gravitational waves in space. These ripples in space-time, caused by colliding black holes or neutron stars, are so subtle that they change the distance between objects by less than 1/10,000th the width of a proton. Detecting them requires isolating test masses from every possible disturbance except gravitational waves themselves. The techniques developed for these fundamental physics experiments have applications throughout space exploration. The precise attitude control needed for gravitational wave detection helps other missions point their instruments with extraordinary accuracy. The vibration isolation systems protect sensitive equipment from the inevitable small disturbances aboard spacecraft. Even seemingly simple tasks like taking photographs in space involve sophisticated physics. Cameras aboard spacecraft must deal with lighting conditions that would be impossible on Earth. On the airless surface of the Moon, shadows are absolutely black because there's no atmosphere to scatter light, while areas in direct sunlight are brilliantly illuminated. The dynamic range between light and shadow is so extreme that no camera can capture both in a single image. Mission planners must carefully choose exposure settings and often take multiple images with different exposures to capture the full range of detail. The cameras themselves must be hardened against radiation and designed to operate in vacuum. Moving parts like focus mechanisms and zoom lenses must work reliably without air for lubrication, and the electronics must function across temperature ranges that would destroy consumer cameras. The images these cameras return have revolutionized our understanding of the solar system. Every planet has turned out to be more complex and interesting than we imagined. Mars has seasons and weather with dust storms that can cover the entire planet. Jupiter's Great Red Spot is a hurricane larger than Earth that has been raging for centuries. Saturn's rings are revealed to be incredibly complex structures with thousands of individual ringlets, shepherded by small moons whose gravity shapes the ring particles' orbits. The moons of the outer planets have proven to be worlds in their own right. Europa's subsurface ocean might contain more water than all of Earth's oceans combined. Titan has lakes and rivers of liquid methane under a thick atmosphere of nitrogen. Enceladus shoots geysers of water hundreds of miles high through cracks in its icy surface. Each of these discoveries has expanded our concept of where life might be possible. The traditional habitable zone around stars, where liquid water can exist on a planetary surface, now seems too restrictive. Life might thrive in subsurface oceans heated by tidal forces, in underground aquifers on Mars, or in the upper atmospheres of gas giant planets. The search for life beyond Earth has become one of the primary drivers of space exploration. Every mission now includes instruments capable of detecting biosignatures, chemical indicators that life might be present. These range from simple organic molecules to complex isotope ratios that could indicate biological processes. The challenge is distinguishing biological signatures from purely chemical ones. Many organic molecules can be produced by non-biological processes, and even isotope ratios can be affected by geology rather than biology. Confirming the presence of life requires multiple lines of evidence and extremely careful analysis. Future missions will carry even more sophisticated life detection instruments. Some will be able to sequence DNA directly. If Earth-like life exists elsewhere, others will look for more exotic forms of life that might use different biochemistry entirely. The possibility that life might be common throughout the universe has profound implications for space exploration and for humanity's understanding of its place in the cosmos. If life is rare, then Earth might be precious beyond measure, the only known outpost of biology in a largely sterile universe. If life is common, then we're part of a vast community of living worlds, and contact with other life forms becomes a real possibility. Either way, space exploration continues to expand the boundaries of human knowledge and capability. Each mission teaches us something new about physics, engineering, biology, or planetary science. Each success makes the next mission more ambitious, and each failure teaches valuable lessons that improve future missions. The international cooperation that characterizes modern space exploration represents one of humanity's greatest achievements. The International Space Station, built by agencies from the United States, Russia, Europe, Japan, and Canada, demonstrates that complex technical projects can transcend political boundaries. Astronauts from dozens of countries have worked together in space, forming friendships and professional relationships that span the globe. This cooperation extends to robotic missions as well. Data from spacecraft is routinely shared among international scientific communities, advancing our collective understanding of the solar system. Missions often carry instruments built by multiple countries, and the results benefit scientists and educators worldwide. The challenges of space exploration are so complex that no single nation can easily tackle them alone. Pooling resources, expertise, and perspectives makes missions more capable and more likely to succeed. It also ensures that the benefits of space exploration are shared broadly, contributing to scientific knowledge and technological advancement around the world. As space technology becomes more capable and more affordable, we're entering an era where private companies and smaller nations can participate in space exploration. This democratization of space access is leading to new kinds of missions and new approaches to old challenges. Small satellites, some no larger than a smartphone, can now perform observations that once required massive spacecraft. Constellations of these small satellites can provide global coverage for communications, Earth observation, and scientific research. The reduced cost and complexity make space-based research accessible to universities, private companies, and developing nations. This proliferation of space activity also presents new challenges. The space around Earth is becoming increasingly crowded, with thousands of active satellites and millions of pieces of space debris. Collisions between objects in orbit can create clouds of fragments that pose risks to other spacecraft. Managing this orbital environment requires new approaches to space traffic control, international agreements on spacecraft operations, and technologies for removing defunct satellites and debris. It's a problem that will only become more complex as space activity continues to expand. The long-term vision for space exploration includes permanent human settlements beyond Earth, mining operations in the asteroid belt, and perhaps eventually interstellar missions to other solar systems. Each of these goals presents enormous technical challenges, but they're all achievable within the framework of known physics. The key technologies needed for these ambitious goals are extensions of systems already used in space exploration, closed-loop life support systems, in situ resource utilization, advanced propulsion systems, and automated manufacturing. What's required is not new physics but new engineering and new economic models for space development. The transition from exploration to settlement represents a fundamental shift in humanity's relationship with space. Explorers visit new places and return home with knowledge and samples. Settlers stay, building permanent communities and transforming alien environments into extensions of human civilization. This transition is already beginning with the International Space Station, where astronauts live and work for months at a time. Future missions to Mars will likely involve stays of 18 months or more, and eventual Mars settlements might house thousands of people living largely independent of Earth. The physics that governs these settlements will be the same physics that governs life on Earth, but applied in alien environments with different gravity, different atmospheres, and different resources. Understanding how to apply terrestrial physics in extraterrestrial settings is one of the ongoing challenges of space exploration. As you lie there in the comfort of your bed, surrounded by the familiar sounds and sensations of Earth, consider that everything around you is made possible by the same physical principles that enable space travel. The materials in your home were formed in the cores of ancient stars. The energy that powers your devices ultimately comes from nuclear fusion in the sun. The electronic devices you use every day apply quantum mechanics to process information. The boundary between terrestrial and space technology is increasingly blurred. The GPS system that helps you navigate uses satellites in precise orbits calculated using orbital mechanics. Weather forecasts depend on satellites that monitor Earth's atmosphere from space. The internet relies on satellite communications to connect distant parts of the world. These connections between space technology and everyday life will only grow stronger as space exploration continues. Materials developed for spacecraft find applications in automobiles, buildings, and consumer electronics. Life support systems designed for space stations inspire more efficient systems for buildings and vehicles on Earth. Perhaps most importantly, space exploration continues to change how we think about our planet and our place in the universe. Every image of Earth from space reminds us that we share one small world, that national boundaries are human constructs, and that the health of our global environment affects us all. The perspective from space has inspired environmental movements, influenced art and literature, and changed how we think about our relationship with nature. It's made real the concept that we are all passengers on spaceship Earth, traveling together through space and time. As space exploration makes its gradual transition from government programs to commercial ventures, and from brief visits to permanent settlements, this perspective will become even more important. Future generations may be born in space, may live their entire lives beyond Earth, may think of themselves as citizens of the solar system rather than any particular planet. Yet no matter how far humanity spreads through space, Earth will remain our home, the place where our species evolved, where our cultures developed, where the vast majority of humans will likely always live. Space exploration doesn't diminish the importance of Earth, it enhances our appreciation for how remarkable our planet is. The same physics that reveals the harsh challenges of space also shows us how perfectly suited Earth is for life. Our planet's size gives it just the right gravity to hold a substantial atmosphere without crushing surface-dwelling life. Our distance from the sun provides temperatures that keep water liquid across most of the planet's surface. Our large moon stabilizes Earth's axial tilt, preventing extreme climate variations. These conditions might be rare in the universe, making Earth a precious oasis in the cosmic dark, or they might be common, suggesting that life could thrive on countless worlds among the stars. Space exploration is gradually providing answers to these fundamental questions about the nature and prevalence of life in the universe. Each mission, each discovery, each small step beyond our home planet adds another piece to this vast puzzle. The robot explorers we send to other worlds are our ambassadors to the cosmos, extending human presence and human curiosity to places we cannot yet safely travel ourselves. And someday, perhaps in your lifetime, humans will take their first steps on Mars, establishing the first permanent human presence on another planet. Those first Martian settlers will carry with them everything we've learned about living in space: how to grow food in alien soil, how to manufacture tools and equipment from local materials, how to maintain physical and psychological health in an environment where one mistake could be fatal. They'll also carry with them the accumulated wisdom of our species, our art and music and literature, our scientific knowledge, our philosophies and religions, our hopes for the future. They'll be not just explorers but gardeners, planting the seeds of human civilization in alien soil. The physics that makes such settlements possible is elegant in its simplicity. The same laws that govern falling objects on Earth will govern the trajectories of spacecraft traveling between worlds. The same thermodynamics that describe steam engines will govern the life support systems that keep settlers alive. The same electromagnetic principles that power our devices will provide energy and communications for communities on distant planets. Yet the application of these simple principles to the challenge of living in space requires some of the most sophisticated engineering ever attempted. Every system must be more reliable than its terrestrial equivalent, more efficient, more adaptable to extreme conditions. There's no repair shop on Mars, no emergency services to call if something goes wrong. This requirement for extreme reliability is driving advances in automation, artificial intelligence, and self-repairing systems. Future spacecraft and space settlements will need to diagnose and fix their own problems, manufacture their own replacement parts, and adapt to changing conditions without human intervention. These technologies will eventually find applications on Earth as well, making our terrestrial systems more resilient and efficient. The challenge of surviving in space is pushing human technology forward in ways that benefit everyone. As you rest there, breathing easily in Earth's generous atmosphere, surrounded by the gentle pull of familiar gravity, consider that you are already part of this great adventure. The oxygen you breathe was created by billions of years of photosynthesis, a biological process that harnesses the nuclear energy of the sun. The carbon in your body was forged in stellar cores and scattered through space by ancient supernovae. The elements that make up your body have traveled across the galaxy before becoming part of Earth, part of life, part of you. In a very real sense, you are made of star stuff, temporarily assembled into a conscious being capable of contemplating the cosmos that created you. Space exploration is ultimately about understanding our place in this cosmic story. Every mission reveals new chapters in the history of the universe, new insights into how planets form, how life begins, how intelligence emerges from the dance of matter and energy. The spacecraft we send to other worlds are messengers from Earth, carrying our questions to distant places and bringing back answers that expand our understanding of everything around us. They tell us about the formation of our solar system, the evolution of planetary atmospheres, the possibility of life beyond Earth. But perhaps most importantly, they remind us that we are all travelers together on this small blue planet, spinning through space at thousands of miles per hour, orbiting a star that is itself moving through the galaxy at incredible speeds. We are already space travelers, all of us, riding aboard the most sophisticated spacecraft ever built, planet Earth. Sleep well now, fellow Voyager. Rest in the knowledge that while you sleep, robotic explorers continue their patient journeys through the solar system, gathering data and images that will inspire and educate future generations. Rest knowing that human ingenuity and the elegant laws of physics have made it possible for our species to reach beyond our home planet and touch other worlds. And rest knowing that the same forces that govern the motion of planets and the fusion reactions in stellar cores are holding you gently against your bed, keeping your heart beating, maintaining the delicate chemistry of life within your body. You are part of the cosmos, and the cosmos is part of you, and that connection makes every moment of existence a quiet miracle. From wherever you are in the world tonight, thank you for joining me on this gentle journey through the science of space travel. If this helped you drift towards sleep, I'm grateful to have shared these peaceful moments with you, and if you're still awake, I hope you found something to spark your curiosity about the remarkable physics that makes space exploration possible, and about your own place in the vast, beautiful, ever-expanding story of the universe. Until our next journey together, sleep well and may your dreams carry you safely through the stars.